Hi everyone. We're going to talk about stoichiometry today. I apologize if I am not here. Means the child is not healthy yet. So I ask for patience as we go through this new topic. Stoichiometry is definitely going to be something that we spend a lot of time on over the rest of the semester. It's going to be applied to a variety of scenarios. But every chemist does stoichiometry, so it's an important topic to really to master. So first off, it's the chemist's favorite tree, of course. All right. Well, I actually have a very relevant way of leading into stoichiometry, and that is by recipes. I am a addict of cookies, specifically this particular recipe. If you look through it, some of you who might also be addicts of these kinds of cookies, you might even recognize this recipe. Yes, it is the Nestlé Toulouse recipe. It is the best. But what does this have to do with chemistry? Well, let's think of it this way. This recipe is essentially it's like a chemical reaction. It tells you all the ingredients of the reaction, right? We have all of these ingredients come together and make this product, 60 cookies. Okay, scenario for you. I've got 25 eggs. This seems like a lot of eggs, but it is not unreasonable for me to have this many eggs in my fridge. And one day, upon having 25 eggs in my fridge, I asked myself, how many cookies can I make from this? But I'm also going to assume I have enough of everything else. Okay, pause the video, take a second. How many cookies can you make? Calculate it out. Alright, so hopefully you paused and you did your calculation. How many cookies could you make from this? Well, lots of you probably didn't do this, but I used factor label method. You probably did the same math, but maybe didn't use the actual method. But let's just do this, just for fun. We've got 25 eggs, right? And I'm trying to convert the number of eggs into cookies. Well, I know I have to have eggs down on the bottom, right? And what better way to figure out how many eggs than use the relationship between eggs and cookies from the recipe? Well, for every 2 eggs, I can make 60 cookies as long as I have all of these other ingredients, right? So I'm assuming that I have a ton of flour, lots of baking soda, lots of salt, butter, and sugar, and brown sugar, and vanilla extract, okay? Oh, and chocolate chips. So I just need 2 eggs to make 60 cookies. So if I put 2 eggs on bottom, my eggs now cancels, and I have cookies on top. So if I take 25 times, 25 times 60, 6 times 2 is 12, 13, 14, 15, 1, 5, 0, 0, divided by 2 is how many? 750 cookies of glory. How amazing is that? To be surrounded by 750 cookies. Oh, that's just the life, right? So you can make 750 cookies. I was able to take an amount of reactant, my eggs, and predict how much product I can make from that reactant. Sounds like something I could maybe use in chemistry, right? I often would want to find out how much I could make of a product based on how much reactant I have. Or vice versa, if I must make this amount of product because I've got a client who is purchasing this compound from me, I need to figure out how much reactant do I need to make. In this 750 cookies business, not completely unreasonable. My mother-in-law just made 44 dozen cookies? That's a lot of cookies. And so she had to go through this entire process. How many cookies or how much flour did she need to buy? Crazy. All right. This is the important piece, though. You used a ratio of eggs to cookies to convert between eggs and cookies. Well, we're going to have to use some sort of ratio in our stoichiometry problems. So, what is stoichiometry? Well, it has to do with doing proportions and reactions. It's all about the proportion of this reactant to this one, this reactant to this product to this product. Okay? Stoichiometry, the definition of it is that it's a mass relationship between substances. This could be reactants and products. It could be just reactants. It could be just products. It doesn't really matter. Okay? So as long as you're looking at the mass relationship between the two substances. It's based on this thing called a mole ratio. So this is where the ratio is coming in. And this mole ratio is going to allow us to do those factor label method problems and molar conversions from one compound to another. So now we're going to be able to predict, based on this many grams of reactant, I can figure out how many grams of product I should make. So the mole ratio, I'm going to show you where you can get it. It's very simple, and it's phenomenally easily defined. Okay, it is actually this. It's indicated by the coefficients in a balanced chemical equation. So we have the equation magnesium plus oxygen. You did this in lab. At least first and second period did this in lab the other day, right? You took your magnesium, you reacted in oxygen, and you made magnesium oxide. Well, remember we were talking about figuring out the mole relationship between the two substances to form the formula? Well, the reaction, if I was to read this out in terms of moles, instead of saying 2 atoms of magnesium react with 1 molecule of oxygen to form 2 units of magnesium oxide, which is actually kind of, I mean, we're not really working on the atomic level necessarily. We're weighing things out in grams, and so there's definitely lots and lots of atoms, right? So let's change the terminology to moles. 2 moles of magnesium plus 1 mole of oxygen gas forms 2 moles of magnesium oxide. So for every 2 moles of magnesium, you need 1 mole of oxygen. That's the ratio. It's a 2-to-1 ratio. Okay? So with those mole ratios, what is the mole ratio of magnesium to oxygen? Well, we just said that. There's 2 moles of magnesium for every 1 mole of oxygen. So I can write it like this: 2 moles magnesium, colon, 1 mole of oxygen. That's kind of how you write ratios, right? Something, colon, something. And this isn't -2. This is just that bullet point that looks like a hyphen. Okay. Now what I can do, I can also look at ratios of reactants to products. So what is the mole ratio of oxygen to magnesium oxide? Well, I look for the coefficients out in front. I see 1 mole of oxygen to 2 moles of magnesium oxide. So it's a 1-to-2 ratio. For every 1 mole of oxygen that's used up, I make 2 moles of magnesium oxide. Okay? So these mole ratios have to come from balanced chemical equations. And this is why it's so very important that you, 1, have correct formulas, so that 2, you can have the correct balancing. Okay? So it's all kind of building together. All of these last few units are very much interdependent on each other. Okay? So we can't find a mole ratio if we don't have a balanced equation. It's not possible. Alright, here's the cool thing. The mole ratio is going to become a conversion factor. Okay? Because it is a ratio, you have something to something. That means we can turn it into a fraction. This 2 moles of magnesium to 1 mole of oxygen can look like this, where it's 2 moles of magnesium over 1 mole of oxygen, or flip it. 1 mole of oxygen over 2 moles of magnesium. Okay? You're actually going to find that this is located on your mole map. Dun, dun, dun. your beautiful, beautiful mole map where you have moles of A to moles of B. The only little difference is the little tiny snafu. Your mole map calls it an equation coefficient ratio. And you need to change it to say mole ratio. So you can cross that off and write in moles. Okay? Mole ratio is easier to say. But equation coefficient ratio tells you really, it's more descriptive of what it is. So the mole ratio is always going to be the conversion factor that gets you from the left half of the mole map to the right half. Okay? The only way to get from moles of A to moles of B is using the mole ratio. So that's what we just found. Its mole ratios are on the mole map. It's called the equation coefficient ratio. So I do want you to write that in, that the equation coefficient ratio is the same as mole ratio. And this is our easy way of getting from substance A to substance B. All of our other conversions we've done so far have only stayed on one half of the mole map. We've not ventured over to the dark red side. Okay, so I want to show you how to do stoichiometry problems very systematically. There's, again, nice, easy steps to follow when you're doing stoichiometry problems, and it's pretty much the same as any factor label method problem you're using. You are figuring out your starting units, figuring out your ending units, line up conversion factors, and cancel units appropriately. Stoichiometry is actually even more simple, I think, because it is very limited in the number of conversion factors you typically use. Okay? So, step one for doing any stoichiometry problem, you have to have a balanced chemical equation. If the equation is written out and it has coefficients already written in, it is probably already balanced. It would be very wrong of me or of Quality Core to give you an equation that had the wrong coefficients. Okay? So if there's coefficients already there, it's balanced. If there are not coefficients, then you need to balance the equation or check to see if it needs coefficients. Maybe it is 1 to 1 to 1 to 1. Okay? All right. Second step, whatever the problem is stating, figure out what things you're given and figure out the units you're starting with. Is it grams? Is it particles? Is it volumes? Maybe it's volume of a gas where it might be at STP, not at STP. What are the units you're starting with? Maybe it's a volume of solution. These are the sorts of units you are starting with. These things that are in the big circles. Okay? And then as you read through the problem, you're looking also for what are you solving for? How many grams? I must be solving for grams. Find the theoretical yield. We'll discuss that a little bit more in a second. How many moles of? It must be moles. So pay attention to the wording, figuring out what it is that you are solving for. Okay? But again, use the factor label method and you're going to use the appropriate conversion factors. The mole map is going to tell you exactly what path to take, and I will give you a sneaky little hint that usually it's from mass of A to mass of B. Okay? On occasion, you'll do mass of A to volume of solution to volume of solution, but notice all of those are 1, 2, 3 steps. Okay? Most often, it's just going to be 3 conversion factors. Okay? And they often are the same 3 conversion factors. Alright, so we're just going to dive into some practice problems. Okay? We're going to wake up the iPad. Going to get rid of that. There we go. Alright. So here's what I see in this problem. I've got a question which states, how many moles of KClO3 must decompose to produce 9 moles of oxygen gas? Well, my first step is to have a balanced chemical equation. And sometimes the equations might be a little bit complicated. I might have to give them to you. I might not give them to you. Well, in this case, we'll work through it. We have KClO3, and that is reacting to produce oxygen gas, and then it has to have something else in it. I'm actually going to move over so I can't always tell where on my screen it is going to show up. So KClO3 is decomposing into forming oxygen gas plus something else. This is a decomposition reaction because you only have one reactant. You have oxygen as a product, and I'll give you a hint. It's actually KCl that's also produced. So step 1 of stoichiometry is to do what? Let's revert back a little bit. Oh, write out a balanced chemical equation. Is this balanced? I see a potassium, a chlorine, 3 oxygens, 2 oxygens. They all stink. Looks like it's not. So I'll put a 2 out in front to give me 6 oxygens. I'll put a 3 out in front to give me 6 oxygens. Now I have 2 KCl's. So I have this. 2 KClO3 reacts to form 3 oxygen gas plus 2 KCl's. Okay. Now, determining the starting units, determining ending units. Let's look at what we've been given. It says how many moles. How many? How many? Oh, that must be what I'm solving for. So I'm solving for how many moles of KClO3. I'm going to put a big question mark under KClO3 and I'm going to write moles. I want to know the number of moles. Okay? Must decompose in order to produce 9 moles of oxygen gas. The only other thing given in the problem is 9 moles of oxygen gas. So that must mean I have 9 moles of oxygen gas. Alright, well, if I go back to my factor, or my pretty little mole map, I know that I am going from moles to moles. So I'm going from here to here. The only conversion factor is my equation coefficient ratio, aka mole ratio. Okay. So what should I do? I'm going to take the number I start with, this 9 moles. And I'm going to be very careful about how I write things out. I don't like cutting corners on stoichiometry. I cannot just write 9 moles. I have to say 9 moles of oxygen. I must state, must label with compound or formula. You must. Okay? So my 9 moles of oxygen gas are going to be reacting to form some, or they're being formed from some unknown moles of KClO3. I need the mole ratio. It's the only thing. This guy here, mole ratio goes through. Okay. Right, well, if I look at my problem, I see that this is a coefficient in the compound that I want, and this is the coefficient in the compound that I want. Okay? So I'm looking for that to go into my mole ratio. So I'm going to put 3 moles of oxygen. Where do they go? The 3 moles of oxygen, because this is my coefficient, the 3, is going to go on the bottom so that the moles of oxygen cancel out. Gone. Okay. Now I'm going to take the 2 moles of KClO3 and put them on top. Fortunately, that means my units are going to be moles of KClO3. So if I take 9 times 2, that's 18. And if I divide by 3, that's 6. So my answer should be 6 moles of, label it, KClO3. And that's our answer. So I have to start with at least 6 moles of KClO3 if my intention is to make 9 moles of oxygen gas. Okay? If I start with 5 moles of KClO3, I will not make 9 moles of oxygen gas. Just like if I start with 3 eggs, I will not make 750 cookies. So there's my equation. Sometimes it's given to you like this. Then you need to balance it. We balanced it. We then identified we needed to form 9 moles of oxygen, and we were trying to figure out how many moles of KClO3 this would come from. We used our mole map. The only conversion factor was the equation coefficient ratio, aka mole ratio. So we set up our factor label method with only one section for a conversion factor. Okay? Only one conversion factor is required. We put our 9 moles on the top left. We put in our mole ratio so that moles of oxygen canceled out. And we solve for 6 moles of KClO3. Sig figs, we start with 1, we end with 1. Okay. So whenever we're going from moles to moles, we use the mole ratio, and that is it. Alright, maybe I'll even note that. So we'll use this color. So moles to moles. Mole ratio is the only thing that you need. Okay? Alright, back to this. This question says, how many grams of silver will be formed from 12 grams of copper? And then the equation is provided. Remember, we did this reaction as a demo. We had the silver nitrate in the test tube, and we have a copper wire that was coiled up into the test tube. Well, this question is asking us to take 12 grams of copper and turn it into grams of silver. Oh dear, small math. First off, do we have a balanced equation? Yes. Balanced equation. Hooray! The next thing, what are our units that we're starting for, or that we're starting with? Well, it's the only thing given in this problem is that we have 12 grams of copper. Okay. So we're going to label that. We have 12 grams of copper, and we are solving for how many grams of silver. This is what we need. Okay. This is a question mark. So we're going from grams to grams. Oh dear, small map, what do you have to say about this? Anytime we're going from grams to grams, we're starting over here in mass, solid, liquid, gas, going zoop, 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 and we're ending over here at mass, solid, liquid, gas. So I see that I need molar mass of A, mole ratio, and molar mass of B. So I'm going to put that over here. So I'm going from grams to grams. I'm going to put grams A to grams B. Okay. I'm going to use molar mass of A, mole ratio of A to B, and molar mass of B. 3 conversions. Conversion factors. Okay? 3 conversion factors for my factor label method. So that means I'm going to erase this part. I'll put it here. 3 conversion factors. That means when I'm setting up my factor label method, I've got my starting spot right up here in the top left. I'm going to have a space for the mole ratio, or for the molar mass of A, a space for the mole ratio, and I'm going to have this last part be the molar mass of B. Okay. That's what's going on with my factor label method. Okay, well, you see this here on my mole map, molar mass, mole ratio, molar mass. All right, so if I'm going to start with my 12 grams of copper, I'm going to put that in the top left. My first thing, it says I need molar mass of A. The molar mass of copper, oh dearest periodic table, copper, where are you? 63.55 grams per mole. Grams needs to be where? On the bottom. So I'm going to put 63.55 grams of copper on bottom, and I have 1 mole on top. So this piece is the molar mass. Okay, I need the mole ratio of A to B. Where do I get the mole ratios? I get them from the balanced chemical equation. We're going to take the coefficients. So I see the coefficient in front of copper is nothing. What does that mean it is? It's a 1. So 1 mole of copper, and am I looking at silver nitrate here? No, I don't care about silver nitrate in this problem. I only care about silver and copper, and that's it. So it's this guy and this guy. So I'm going to have my 1 mole of copper for how many moles of silver? 2. I'm going to put moles of copper so that moles of copper cancel. That means moles of copper has to be on the bottom. So I'm going to have 1 mole of copper on the bottom, and then my 2 moles of silver on top. And now my moles of copper cancel, just like I wanted. Alright, so now I have moles of silver. I don't want moles of silver. I want to turn that now into a mass of silver. So the last piece is to use the molar mass of B, as shown in my template over here. Molar mass of B, well, B is silver, so I just go to my periodic table. I say, oh dear silver, how much do you weigh? 107.9. Okay, that's grams per mole. I have moles on top. I want moles to cancel, so I want moles on bottom. That means I have my 1 mole on bottom, and my 107.9 up on the top. And then this one has more decimal places. It doesn't matter. Okay, so 2 decimal places is usually the minimum, except for some of these are heavier and don't have enough space on the periodic table, I guess, is the reason. I don't know. So there's 2 moles of silver on top, moles of silver on bottom. That now cancels. Okay. Now you just need to get out your calculator and calculate it. 12 times 2 times 107.87 divide by 63.55. Take a second, calculate it out. Pause the video. Alright, so as you calculate it out, hopefully you got 40.7 grams of silver. I started with 3 significant figures. I'm ending with 3 significant figures. Okay, so that means if I have a 12-gram piece of wire of copper, and I had unlimited amount of silver nitrate, I could plate out 40.7 grams of silver. You can then go look up what's the price of silver now and see what kind of rate you could sell that silver as. There's a child crying for her mommy. We'll see how fast we can go. Okay. One more problem. When 45.8 grams of K2CO3 react with excess hydrochloric acid. Oh dear. She's really screaming, guys. I'm sorry. Okay. We'll come back to this.